No.
Okay. Start the last lecture of Professor Dirac, and I think it is about quantum algorithms.
That's right, yeah. Okay, so I'm going to talk today about quantum algorithms, but I want to remind you a little bit of the setup that we have. So I was mentioning So yesterday I started talking about quantum information in many-body systems, and so I said that many-body systems, in a way that sometimes appears in some field of physics, like in condensed matter physics and lattice Lie theories and some other formulations, can be casted a little bit in the language of quantum information. And in this particular way of looking at them, what you have at the end is something like a lattice, which could be in any dimension, like in 1D, it would be like a string. The dimensions could be a square, or rectangular, or triangular, or Cagonel lattice. There are many lattices, or 3 dimensions. And then you have at each of your vertices of the lattice, well, actually, it can be even more general, we didn't talk about it here. It could be a graph with vertices and edges, and each of the vertices, then you have some Hilbert spaces, and these are typically spin Hilbert spaces or finite dimensional Hilbert spaces. And now you can have some Hamiltonian that describes the interaction between the spins. You can also have some other formulations in which you have, instead of spins in the vertices, you can have fermions. You can associate fermionic operators to each of the vertices. And then you will also have a Hamiltonian which describes the fermions moving on the lattice and interacting with each other. Or you could even have not only degrees of freedom on the vertices, but also on the edges, and then you can describe in that way things like lattice Lie theories. So at the end, I mean, what you have a formulation, and you can write some system on a lattice, and you have a Hamiltonian, and given that this Hamiltonian is typically local, meaning it's a sum of Hamiltonian which are acting on some regions of the lattice, then you can ask questions like, what are the physical properties that you predict in the dynamics or in thermal equilibrium? And by physical properties, we mean that we can take observables, operators, or joint operators acting on these Hilbert spaces on the vertices or on the edges, and we would like to know what are expectation values of these observables. We would like to predict what are expectation values of these operators in some particular states. And those states, I describe 2 kinds of states. The dynamical states, in which the problem is formulated that you have some initial state that is given, and you want that under the evolution generated by the Hamiltonian, so e to the minus IHT, acting on the state, that's the state for which you would like to make the physical prediction. You would like to compute expectation values. Or it could be in thermal equilibrium, in which you're giving on top of that a temperature. Then what you're interested is in the Gibbs state e to the minus beta h, properly normalized, and that's the state which now is a mixed state, and you would like to compute expectation values which are computed with a trace of this operator with the corresponding observable. And so that's how the problem is formulated, and you can formulate a little bit more, let's say, more precisely. If you start just saying so that you have some number of lattice sites, you have the geometry, and you're giving some prescription on the error that you allow, some epsilon, and then what you would like to know is given some algorithm that would solve that problem, to say what is the computational time that it will take to solve that problem, to that precision epsilon. And now you have different classical algorithms or different quantum algorithms, and if you take the best classical algorithm that you know, the one in which the scaling of the time with the size of your system, or with 1 over epsilon, or whatever, it's the best in some sense, then this will define where your problem is in this complexity class that I told you yesterday. So if this best algorithm grows only polynomially with the system size with n, the number of vertices that you have in your graph, then you say that the problem is in P. You formulate properly as a decision problem. And if it's not, but you can verify that it's it takes exponential time, it takes more than polynomial time, but you can verify it with polynomial time, with some certificate, then it's in NP, and so I define the classes. So you can now take the quantum algorithms, you take also the ones that exist, you take the best one that is known for that problem, and this will tell you now in which complexity class it's with the quantum algorithm. So I define the complexity classes like QP and QNA, that were the basic ones that are new in quantum, and so what you classify, then it may happen that it's that, well, what I say is that the classical algorithm will be at least as good as the quantum algorithm will be at least as good as the classical algorithm, because quantum algorithms include all classical algorithms. So with the quantum mechanics, you can indeed do everything at the same, let's say, time scale that in classical mechanics. You can avoid the superposition, there are systematic ways of doing that, but it may be better. And then in that case, you will say that you have quantum advantage or whatever, or that the complexity class is better. And so I started just with the problems that I mentioned the other day, the dynamics, the finite temperature, the thermal equilibrium, and the ground state, which is a particular case of the thermal equilibrium at zero temperature. And so I gave you, so when I was formulating, I told you in which class they are, each of them. And then yesterday in the afternoon, I said, well, now let's try to see with classical algorithms ways of solving those problems. I said that there were many, and very, very good, and they make that many problems can be solved, but there are some problems that can't be solved efficiently. So these they will be in the class VPP, the ones that can be probabilistically be computed efficiently with a classical computer. And what I gave you was specifically describing some particular way of solving these problems with so-called tensor networks, which is a technique which is inspired in quantum information, that has the perspective that you look at the state of your system, this psi or rho, this dynamical state or the ground state or the thermal state, the thermal equilibrium state, even though it requires an exponential number of parameters, it requires an exponential memory in order to store it in a computer. With tensor networks, under some conditions, then you can have a more efficient description. So you only need a number of parameters to describe the state that is polynomial in the size of your system. Remember that I say that if you just write your state in any product basis, then in general you will have 2 to the power n, you have qubits coefficients, complex coefficients, whereas if you write it in terms of a tensor network, and this turns out that the state is in this corner of Hilbert space that I mentioned yesterday, then you can write it in terms of a polynomial number of coefficients. And so this, on the one hand, when it gets around for certain problems, is this exponential increasing of the memory that is required for classical methods. Now still, there is the second hurdle that you have to overcome, which is the time. So it's still maybe exponential time. And so I talked about some algorithms, classical algorithms based on tensor networks, which promise that the time will also be polynomial, and some heuristic algorithms for which people have not proven, but the practitioners, they use them, and they work in some particular way. And then I said, well, but this tensor network description, actually, if you look at it, what you're doing is that you have a many-body system living in a huge space, this big dimensional Hilbert space, and at the end, the whole many-body state can be described in terms of a single tensor. So you have homogeneous systems, you have translational invariant systems, then a single tensor will tell you about all the properties of the many-body state. So in principle, it should be possible to encode in this tensor the physical properties of the whole many-body state. You will not have to go to Hilbert space, but by looking at your tensor, then you can gain information about this complex state. And I gave some examples of that. So I say that if you have symmetries, then your tensor will have certain symmetries. Now, of course, the symmetries in Hilbert space are simple in the sense that they are usually described in terms of representations of some groups. If you go now to the tensor and look at the symmetries, then it's much simpler because there is a single tensor, and it gets a little more complex because then you have projective representations of that group, which makes things a little bit more mathematically complex. You have gauge theories in your group, so you have gauge symmetries. Then you can look them up also in terms of the tensors, and then they will look at some other kind of symmetries of your tensor, which will be a little more difficult. But however, the price that you have to pay is very little as compared to the price that the other state has many coefficients, is huge, and here you just have a single tensor. And in the same way, you can look at topology. Certain kind of criticality and so on can be encoded in the tensors, and you can find a dictionary. So giving a tensor how to find these properties, and I just gave you some ideas. And I mentioned that you can look at many papers that are in the literature on not only how to use tensor networks computationally for numerical methods, but also to classify phases, to describe topological order, to make this bond boundary correspondence, and so on. So today, what I want to do is to shift to the second methods, the quantum methods, the methods based on quantum algorithms. And so the problem will be the same. So the formulation is the same as I proposed on the first day. Either we all will have a lattice, and so typically have a regular lattice, but it could be a graph, so it could be something that is irregular, that doesn't matter, but make things simple, talking about the lattice. We will be given a Hamiltonian that I will assume here that is local, and I meant people, the context of quantum information, they call it geometrically local, meaning that it has a finite range of interactions, in language, more physical language. And then we're interested either in the dynamics, so we will given some state, initial state, which typically will be some easy state, in quotes, something like a product state, so state that is very little entanglement or that has no entanglement at all. I defined already what was entanglement. And then we will be interested in the dynamics generated by the Hamiltonian and some expectation values, so some physical property that we want to predict with that. And then the second problem would be thermal equilibrium. So you're again, I'm giving the lattice, I'm giving the Hamiltonian, I'm giving some observable, I'm giving some predictor, some prescription for the errors, I'm giving maybe some temperature. And what you would like to compute is the expectation value of this observable with this given state at the temperature, and to have it up to some error epsilon. And in both cases, both in the dynamical or in the thermal equilibrium, so you're interested in knowing, so what's the scaling? You don't want to solve it for 3 particles. We would like to see if we make the system bigger and bigger and bigger, so whether the computational time will grow exponentially with n, or maybe it grows exponentially in 1 divided by epsilon, okay, so then in the error and so on. And so that's the game that we have in mind. Now, the plan for today is that I will give you algorithms that solve these problems, and some of them will be very simple to understand and are very basically that Feynman had in mind, that you're given some problem that you would like to compute some expectation value with some state that is prescribed in terms of your Hamiltonian or anything. Then you take the quantum computer and you prepare the quantum state in the quantum computer, and then you measure the observable. And then you do it many times, and then at the end you take the average of the observable, and this is the prediction. And if you do that, then we know what is the convergence, we know how is the error, and we will know what are the computational times. That's the typical and the simplest method. Now, for some of the other problems, then it will not be possible to do something like that. And so we'll have some other algorithms, and these algorithms, some of them will prepare the state, and some of them will not prepare the state, and it will get more complicated of how to get the information, which is this expectation value. You don't have to prepare the state, you just have to compute the expectation value. But the quantum computer can help you, maybe as a subroutine that gets around some of the problems that you have in the classical, let's say, algorithms, and use this quantum computation to speed up the part that gives this exponential slowdown with the classical computers. Okay, so that's a little bit the plan. And if I have time at the end, so I hope that I have time, I will go then include the errors. So what happens if the quantum computer is not perfect? Because the quantum computers that we have, and we will have for many years, will have errors. And I want also to understand how the errors will affect the answer that the quantum computer gives to these problems, and still whether you can get some advantage if you have these errors in the scalings. Okay, so then I'll start just talking. So this is third part. This is quantum algorithms, and I start with the first part, which I'll talk about the dynamics. which again, I have a lattice. I'll talk about, so I will talk about qubits, but you're interested in fermions or lattice gauge theories, and everything will translate. You just have to put the corresponding lattices and the fermion degrees of freedoms and so on. So I will talk about spins because it would be much simpler to formulate, but everything that I'm going to say, everything applies to not only spins, but also fermions and fermions and interacting with some bosonic systems and so on, fermions with spins and so on. So we have the lattice, we have the Hamiltonian, which is a sum of local Hamiltonians that act on plaquettes or something like that, or nearest neighbor interactions or whatever. And now I'm giving some initial state. And to make it simple, I will consider that we have with some product state. Some product state, so it means that we have something like that, a product of phi I from I equal 1 to n. So this means that the first qubit I can assign the state phi 1, the second phi 2, the third phi 3. So I can assign a Q state to each of the qubits, and therefore the state, according to the definition that I told you yesterday, that's a product state. And I give you some time, t, that I'll call t. That's not the computational time, so that the time that I want to, in which I want to make the predictions, I want to know what is the evolution after this time. And I give you your observable that I'm interested in, which typically will be some local observable or some correlation function that I told you yesterday, maybe acting on some site. And I give you this prescription about the error that I want to have in predicting this observable, because these problems, when you cannot, even classical problem, you cannot get infinite digits, right? So you have to give some prescription about the error they will have. And so the first algorithm for the dynamics was introduced by Seth Lloyd in 1996, and was basically reading off what Feynman was saying in his paper, and formulating in a quantum mechanical, in a quantum computation language, and also doing the calculation explicitly to show that it was very efficient. And so the idea is what I told you before. The idea would be, first you prepare a state, and the state is the product state. And a product state can be easily prepared because if you start, for example, with all your qubits in 0, 0, 0, 0, 0, 0, then you take this qubit and then preparing the state phi 1, this qubit and preparing the state phi 1, and this requires a single qubit gate here. Then this into phi 2, you apply a single qubit gate, okay? So you can do that just with a depth 1 circuit. You act with a single qubit gate to all the qubits, and this is just the depth 1 according to the definition that I gave yesterday about the depth of the circuit. So with a depth 1, so with a cost of 1, let's say time equal 1, then you just prepare the state. So this doesn't count to the scaling, so you have your initial state. And then the idea now is when you have this initial state prepared, what you would like to do is to now evolve your quantum computer according to the Hamiltonian. So ideally, what you would like to have is this state here. And you're able now with quantum gates to have dynamics of your state, or to transform your state into this state here. This is the state that you would like to have. Or something that is very close, that is epsilon close to that state with some distant measure. Then you just have to measure the observable here, repeat it many times, and in this way you will answer this question, and then we know what are the scalings of everything. So the question is, how can you, in a quantum computer, change your state according to this operator that is here. And the tools that you have at hand in a quantum computer are this universal set of gates. So you would like to describe now in terms of the set of universal gates. And the idea is very simple, so I'll do it like I did yesterday when I was talking about the description of thermal states in terms of tensor networks. I was saying that you can first consider the case in which the Hamiltonian commutes, then you understand how it works, and if they don't commute, then you make them commute. And so let's do the same thing here. So let's start with the first case, in which let's assume that all h lambda commute. This is very restrictive. Okay, so typically this will not be the case. Okay, but you will understand. We will learn how to do that with this kind of, in this case, and then in the general case where they don't commute, then we'll do something similar. And so in this case, that's very simple, because then you can rewrite e to the minus I ht as the product of e to the minus I h lambda times t, with lambda, lambda of all these points of your lattice. And now you realize that this operator here is an operator which is only acting non-trivially where this Hamiltonian is acting. So if you take one of them, it will act here, only on these 4 qubits, and another one in another 4 qubits, and another one in 4 qubits. So this means that each of them is a unitary operator which is acting only on few qubits, constant number of qubits that does not depend on n. It's 4 or 3 depending on the range of your Hamiltonian. So each of these is some unitary operator, and we know that any unitary operator can be decomposed in terms of single and 2 qubit gates. We say that is universal. And so this means that in the qubits where it's acting, for sure it can be written now at some single qubit gates, and maybe this control NOT gate. And something that I mentioned yesterday, that I didn't mention yesterday but I should have mentioned, is that it can be easily shown that the number of gates that you need to create an arbitrary operator, I think I mentioned, is 2 to the power the number of qubits that you have. So since we have here a constant number of qubits, the number of gates that we will have, so the circuit depth of each of them will be 2 to some number, which is a constant, so it will be constant. It depends only on the range of the Hamiltonian. It does not depend on n. So this means that we can do this operation now. Each of the operations, each of these unitary operators, one after each other, and each of them takes just a constant number of gates. So the total number of gates that we will have will be this constant times the number of operators that we are applying. And the number of operators that we are applying is the number of terms of your Hamiltonian, because for each term in your Hamiltonian, we're applying one operator. And the number of terms of your Hamiltonian is the number of qubits, because your original Hamiltonian has the different bridges around each of the qubits. And so here there are n of those. So this means that at the end, the number of gates that we have altogether, it would be n times a constant, would be proportional to n, so we don't care about constants, so this is why I put n. And with that, we will have prepared the state, and we have prepared the state, then we measure, and we'll obtain some value for the observable, which will be one eigenvalue of the corresponding operator, corresponding to the rules of quantum mechanics. And now, we do it once, we repeat it again, we repeat it again, we repeat it again, and so we are now sampling according to some distribution and computing some expectation value. And so we know that we will converge to the expectation value, and the rate of convergence, we will do it n times. The scales like the variance of the observable that you're measuring, so that's the range of your spectrum, basically, of observable, which is of the order 1, because you normalize the observable in such a way that the eigenvalues are between -1 and 1, so it's 1, basically of 2, and divided, so the error goes like the variance 1 divided square root of n. So you want this, so this will be the error that you will make if you have n repetitions of the experiment. So if you want to have this equal to epsilon, that's the prescribed errors, it means that m has to be proportional to 1 over epsilon squared. And so we have everything that we have. So the computational time with this quantum algorithm for commuting Hamiltonians would scale like n 1 over epsilon squared, would be independent of t. It doesn't matter how much is t, the time that we have here, and that's what it is. So it's linear in n, and like inverse. Okay, so this is the commuting case. That's the simplest case. But if we understand this, then we can go to the general case using the trick that we also used yesterday. So let's consider now the second case. Where we have that they don't commute, and therefore this is not true. So we cannot do that. Right? The exponential of the sum is not the product of the exponentials if these operators don't commute with each other, so we cannot do that. But what we can do is what we did yesterday, which is typically known under the name Trotter expansion or Trotterization. And the idea is to write this as e to the minus I h t divided by L to the power L. Now, it is possible to write because h commutes with itself, and therefore you have e to the 2h is the same thing as e to the h times e to the h. So they commute, so we can write it like that. And now, if we take each of these terms, now you see that if I would like to write, so you have e to the minus, and you write it like that. For example, I have h1 plus h2 times t divided by L, where h1 and h2, they don't commute. Then you can use things like Campbell-Hausdorff formula for this, and this can be written as e to the minus I h1 times t divided by L, t to the minus I h2 t divided by L, and here it will appear the commutator of these operators in first order of the Campbell expansion, and this operator that is here and this operator that is here, if you complete the commutator, would be something like minus the commutator of h1 h2 times t squared divided by L squared. And you see that if you make L bigger and bigger and bigger, then you will have to repeat it L times. However, the error goes down like L squared. So by making L sufficiently large, then you can forget about that. Incorporate it in the budget of your epsilon, because at the end you're allowed to put some epsilon, so somebody gives you some epsilon, then you have to make very large. So what I'm saying, you make it mathematically rigorous. Okay? You don't use Campbell-Hausdorff, you use inequality between operators that tells you that you can approximate the difference between these two is upper bounded by something and so on. But let's say we wanted to give you just the idea. Now there is okay, so if I do it in general, so if I have e to the minus I sum of h lambda times t divided by L, then we can rewritten as the product of e to the minus I h lambda t divided by L. And here you see that there will be the sum. This will be the commutator in first order. There will be h lambda prime times t squared divided by L squared. And now, you see, if we want this error to be small, we can basically count the terms. So we know, these are operators, and they are bounded, all of them. So they are bounded by 1, let's say, if we normalize the Hamiltonian. And now we start doing the commutators. And what is important here is that when these operators have some overlap, the commutator will be different than 0, but when they don't have any overlap, they will be 0. So out of these terms here, there are n squared terms, right? Because we have n terms and n terms, and all possible commutators will be n squared terms. Only the ones that have overlap will have a contribution to the commutator. The commutator of two operators that are acting on different sides, they don't have any overlap, are 0. So out of those, only the ones that are overlapping will count. How many are there? Well, for each operator lambda, it's only the ones that are around. So it's a constant number, and therefore all the terms that are different than here is proportional to n. So there are n of those. So if you want the norm of this commutator, sum of commutator, is upper bounded by a constant times n. And so you see here you have t squared divided by L squared. You want this to be epsilon, very small, then you have to choose L squared is equal to t squared times n. And L squared has to be t squared times n. And then you put a big constant, and something that will depend on epsilon here. And so you see that L has to go something like t n. And so from here, you do it rigorous, then you see that at the end, this L scales polynomially with n and polynomially with t at the end. Yeah. Yeah. Right. So now, if you do it rigorous, then it turns out that there are higher powers that appear here. Okay, because you cannot only take care of the first order throttle expansion error, you have to make sure that for all the errors and so on, but when you do it, you will get some other power by 1/2 plus epsilon or something like that. Doesn't matter. So what I want to show is that the number of steps that you have here, L, has to be polynomial in T and polynomial in N. And so now, what you can do is erase that according to what you say. We can rewrite the whole thing. Now, each of the term is equal minus h1 t divided by L minus I h say n t divided by L. Then the same thing, L times. Right, so they're all together L times. Would you say that was poly and T, and you take careful also depending on the error budget that you have. And so now you see that these are acting only on few qubits. So we can use what we did before for the commuting. We're back in the commuting, so each of those is acting on some fixed number of qubits. So the number of universal gates that you have here will be constant. You can't count. That here you have n of those, and you have L of those. So the total number of gates is n times L. But L is polynomial in n, and in t in epsilon. So the total time of the computation for the general case scales like, and if you do it correctly, it gives you something that scales like n squared t squared 1 over epsilon squared. So still it's polynomial in everything. Now we could compare, so this means that this problem is in BQP. It's efficient with a quantum computer. And it's not inefficient, it's very, very efficient, because now we could compare with the classical methods. And classical methods, you have the exact diagonalization of the lances that I was telling you yesterday. And this is scaled exponentially in time, but it requires also an exponential memory, because you have to keep at each time step. So this was this double exponential, whereas here there is no exponential neither in time nor in memory. It's linear in memory. You need n qubits in order to simulate n qubits, which it requires, and in time it requires something that grows like that. And this is why tensor networks don't work in this case, because in this case you have dynamics. I mentioned that you will have volume law that I said yesterday, and you have volume law. Tensor networks are useless, are not better than exact diagonalization. So this is a problem where you have a huge advantage. You compare a quantum computer with a classical computer. And that's why you will hear often that quantum computers probably the most clear application where they have the most advantage with respect to classical computer is in the dynamics, in computing on predicting the dynamics of quantum many-body systems. Okay? So I mentioned that if anybody wants to ask a question, I'll be happy to answer. Yep.
There is no consideration on quantum fluctuation in this. I mean, if you have some computing observable, you have some quantum fluctuation coming in the...
No, the quantum fluctuations are taken into account in the fact that you have to repeat many times the expectation value, the error, so the quantum fluctuations will go, like if you have any random.
So you have to consider, when you make your error budget, you have to consider that there is maybe an intrinsic limit in the error.
Well, what I said is that you will have to repeat it m times to get the expectation value. And the m, the number of times, is scaled like 1 divided by the prescribed epsilon squared. This is coming from quantum fluctuations if you want. That's there. Any other question? Okay, so that was the easy case, which is the dynamics. And so now we will consider the other cases, that would be, the algorithms would be complex, but they will rely on this algorithm. So now, to compute equilibrium properties, many of the, or most of the quantum algorithms actually use dynamics. So basically, what you would like to do, maybe you want to consider the ground state, you would like to prepare the ground state, and therefore you have a Hamiltonian that would bring you to this ground state, and therefore, if you're able to simulate the dynamics efficiently, then you will be able to run that Hamiltonian. And so I didn't mention it here, but I should have mentioned, is that I consider here a time-independent Hamiltonian. But if it's the time-dependent Hamiltonian, you can do exactly the same thing. Everything that I did works. You will have to use time order operators and everything else, but trotterization and anything else works perfectly fine, and everything scales, and so this also works for time-dependent Hamiltonian. So your h lambda now dependent time, each of them, you can use exactly the same algorithm. Okay, so I will consider then ground state. And I'll remind you what is the problem. So again, we are giving the lattice, which is specified. We are giving, so this is the lambdas we want. We give n. We will give you the observable, and we'll give you the precision. And so now, let me just explain why this problem is much more difficult in a different way. So, if we consider now, and the Hamiltonian, of course, which is some Hamiltonians, like before. So, let's consider something that people use very much in many body physics, statistical mechanics, which is densities of state. So, let me take the Hamiltonian, and let me consider the spectrum of the Hamiltonian. I mentioned something related to that yesterday. So, this is the spectrum, so I write here the energy, and then I have to put all the eigenvalues here on this spectrum. And if we have qubits, then the number of states that will appear here will be 2 to the power n. Right? So the number of eigenstates is the dimension of the Hilbert space, and the dimension of the Hilbert space is 2 to the power n. So that's the number of lines that I will have for the spectrum. Now, since we have n terms here, and each term is bounded, so of this operator is bounded by a constant, by 1, for example, and it means that our spectrum will run from minus n and n. So we have here minus n times some constant and n times some constant. So you see that we have to fit an exponential number of eigenvalues of our Hamiltonian in some linear size in n. So now it could happen that they are completely random. However, this is not the case. You have a local Hamiltonian, then it turns out that this spectrum has the accumulation of the eigenvalues, all of them at the center. So, I mean, people have shown many years ago that this looks more or less like something like a Gaussian, like that, meaning that here there will be some eigenstate, another one, and they are accumulating more, and there are many. So you take some interval, count how many states, and plot for each interval how many states, then you have the curve, which is the density of states, and this density of states have all the states basically in the center, and the width of this Gaussian is proportional to square root of n.
So you're not assuming the degeneracy of states.
Well, it could be degeneracy.
So
Yeah.
the peak of the Gaussian is not because there are many, because you are more defined, you are
Right. I mean, at the end, so this could be a discrete spectrum. I mean, this is a discrete spectrum,
Yes.
and if you don't have integral systems, then the discrete spectrum will go to the continuum, so that you could well define what is the density of states just by counting and taking epsilon to 0 and to infinity and so on. So that's what I'm plotting, but I don't want to give details. But what is important is that you can show that, let's say, most of the eigenvalues are in the center, and then you have here some polynomial tails. So that there are very few here. There is the ground state, the density of states grows polynomially, and then it gets, all of them are at the center, and this is coming from the fact that your Hamiltonian is local. Okay, so you can, I mean, it's...
Which boundary conditions are you assuming?
It's independent of the boundary conditions. Independent of the boundary conditions, it would be a density of state as all of them in the center if you have these, even if you have random Hamiltonians or anything else. And
the only assumption is locality.
The only assumption is locality. I just want to give a qualitative argument why it's difficult. So now, what you can do is to look at intensive quantities. So not the energy, but the energy per lattice side. So you can divide everything by n. So then this will go from -1 to 1. And the width will be then 1 divided square root of n. So now, if you increase the number of the size of your system, then this is getting narrow and narrow and narrow, and in the thermodynamic limit is basically a delta function. So what will happen is that as you increase n, all the states will be here at the center, because it's getting like 1 over square root of n. However, we are asking questions about this state here. So out of the 2 to the n, or low energy, we'll single out 1. And so it's very difficult. It's like you have a nozzle, right? That you want to go to one state, you want to prepare one state, but typically you have those states here. So you start with an algorithm, then typically we'll start somewhere here, take a random state, a product state will be here in the middle, and then you start just evolving, it will move here because it will be very difficult to find what is the path to go to that state. And this is what is behind this QMA hardness that I told you before, that in general, these problems of getting into the state is hard even for quantum computers because there are very few and then you're trying to go there. And this happens also in finite energies or finite temperatures. You fix some energy density, this one here, which is not the ground state, then in order to get here, make it difficult because of that reason. So I see that I'm going to slow. But thanks, I want to show, so what is this? So I want to talk about a few algorithms for the ground state. And so the first one is an algorithm that always works. So that will promise you that you will find the ground state with a very high probability and then converge. However, it takes an exponential time. And this is not so weird that it takes an exponential time because we know that a general problem, if you don't add physics there, you don't say there are some conditions provided by physics, is exponential time because it's a class of QMA hard. No? And so the idea is a relatively simple algorithm to understand, but it has certain details. So the idea is that you just take a random state. Okay, just take a random state which is a product state. Then we call it psi0. Now this psi0 can be written in the energy eigenbasis. So you take H is equal, so the H E is equal to EP. So let's take all the eigenvalues and eigenvectors of my Hamiltonian, and I mean they can be degenerate or not. So I mean let me assume that they are not degenerate, but you can do it with degenerate, so it doesn't matter at all. So I can write this now as a linear superposition of these eigenvectors. I can write it in this basis. If you want, this is nothing other than E times psi0. So in principle, I can write it in this form because it's a basis. And now, let me measure the energy. Imagine that I can measure the observable, which is the energy. So the Hamiltonian is Hermitian, and therefore it can be measured. So in principle, I could measure this observable. Now, if I measure an observable, two things will happen. I will obtain the eigenvalue with certain probability, which will be this coefficient squared. And if I measure in a filtering measurement, then the state after the measurement will be the corresponding eigenvector. So this means that if I'm able to measure the energy, then I will obtain maybe the first time some energy, and the value, the state after observing it will be the corresponding eigenstate. And I can do it many times. So how many times? I do it to the 2n times. So this means that typically I will get all the energies. And you can see that if you do, some polynomial times 2 to the n times, the probability that in one of these measurements I get the ground state is as large as big as you want. So this means that if I note the first time E1, E2, and then I complete it, if I get in the next round an energy that is larger, I forget about it. I only keep the smallest one. And then I repeat it, I had one energy which is smaller, then I keep it, and I notice. And because I don't want to, write down all the energy, but there are 2 to the n. I don't want to use an exponential memory. I'm just taking this and continue. If I repeat it many times, I can have a probability as large as I want, that I will have the energy of the ground state. However, of course, since I have repeated, the state is gone because I didn't keep it. Well, but I can repeat it, and once I know what is the ground state energy, I can repeat it again until I get it again, and when I get it again, I will have the ground state. And once I have the ground state, I can measure the observable once. This is not enough. I have to measure many times, so I repeat it again, but you see that I will have the total number of time will be polynomial n times 2 to the n. And so this is an exponential algorithm which is able to answer the problem with a polynomial memory. So at the end you don't use any exponential memory, and so that solves the problem. Of course this is not satisfactory because first of all it takes an exponential, but second is how do you measure the energy? And so because with this is an observable which is very difficult to get. And for that is where you use the quantum computer. There is a quantum algorithm to measure these observables. And I will not have time to explain it here. It's called quantum phase estimation. And so let me explain what is the main idea. So the main idea is that what you do is imagine that you have some unitary operator. And what you want to do is to compute now the spectrum of this unitary operator. The spectrum of the unitary operator are just phases, right? Unitary operators or roots of 1. And so what you can do is you take your quantum circuit and you take an auxiliary particle, which you call ancilla, and what you do is a control unitary operation here. So you take an ancilla first in the state plus, okay? And then it does control u. So this means that if the state of the ancilla is 0, you don't do anything, and if the state of the ancilla is 1, then you apply a unitary operator to the rest of the qubits, and the other qubits are in 0, all of them. Okay, so this is the n qubits where you are applying your u. You put an extra 1, and then you do that. Then you do control u squared. Then you do a control u to the 4, and so on. And once you have done these things, then you have to do some Fourier transform. There is a quantum circuit which is called quantum Fourier transform that can be efficiently done with a quantum computer and do some measurements with that. And as a result from that, what it happens is that if you have a sufficiently large qubit, then you will end up with one of the, you project into one of the eigenstates of these u's, and then you have and you can get from there also what is the eigenvalue into the I file with the probability in the state file. So that's the quantum phase estimation. So as I'm saying, it's a standard algorithm in quantum computation, which basically you have a unitary. You can apply control unitary, and then you can apply many times. Then you can get that. So the idea, finishing now, is that so what you do is that you take mu is to the minus IH. And so then you can evolve with it to the minus IH times whatever t that you want here, because this is the dynamical algorithm that I told you before. Now you have to control, but it's easy to show that this control does not take much more than doing the algorithm that I told you before, but the dynamics. So this is something that you can do as long as you can do the dynamics. This is something that you can do as long as you can do the dynamics. This is what you can do. And at the end, this algorithm is equivalent to having measured the energy. And if you measure the energy, then you have what I told you before. You just know that, and so this is an exponential algorithm that, if with all the tools in terms of 2 qubit gates, will give you the solution of your problem, but it will take an exponential time. So what I want to do now in the second lecture is and it cannot be better than that. Okay, because we know that this is a problem that takes exponential time, but this is an algorithm that does the job in the promised time. So now what I will do is that I know, just a second. Okay. So I will tell you so another algorithm that is much more efficient than this one here, as long as some properties, physical properties or Hamiltonian, are taken into account. Okay.
That you have some degree effect in your physical system. How has this affected?
I mean, this is what I'm going to talk at the end. And so what happens is that basically your Hamiltonian that is here will have some terms here, and then that's very bad because you see that the number of terms that you have here scales like n. So you have some error and some coupling to some environment, lambda. Each of your qubits is coupled to some environment. And then the norm of this operator is n. And so you have an error, your Hamiltonian, that scales like n times epsilon. So after a time 1 divided by n, things will be orthogonal to what you have. However, and that's the claim that I'm going to make at the end, this is an extensive error. If you're interested in intensive quantities, you want to measure intensive quantities, like the operators that we have here are all intensive quantities, are single particle operators. Then it turns out that this factor of n goes away and your error in the observable will be epsilon, will not be epsilon times n. So as long as the coupling is small, then you can deal with it.
Now, I don't know. What is a quantum Fourier transform? It is not short.
Is it the one that is using short?
Huh?
Short algorithm will use the quantum Fourier transform. Is the one that gives you out of, because I have to get it right. So if you have a state n, this goes to 1 divided by the square root of m sum e to the I 2 pi divided by n times n dot m times m. So it's the Fourier transform.
Okay.
Discrete Fourier transform. Right. I mean, this now you have to count from 1 to 2 to the power n and so on. It's normal Fourier transform. But this can be done efficiently. That's what this was done in Shor's algorithm. It's the normal Fourier transform. You see here you have the time.
You can do it in an efficient way.
No, exactly. So you have a time sequence. You have to get the spectrum. So you do the Fourier transform, and this is why it works. I don't have time to explain in detail. But this is the standard one. It can be done efficiently because Shor already showed that it can be done efficiently.
Okay. See, it's a kind of a short question. It's a brainstorm question. So that way, so u to the power 2, u to the power 4, and quantum Fourier transform is a way at the end to measure in the basis of the Hamiltonian H. But to measure in the basis of Hamiltonian H, one need to bring 0, 0, 0 to the basis of the Hamiltonian H. So if this algorithm is polynomial in n, this gives an integral.
No, it's not polynomial in n. So you will have here an exponential in n to get some epsilon. Okay, so you have here many powers, and you see that it's the number of times that you do it is polynomial, but you're doing an exponential of this number, so the total time when you have to run your algorithm goes exponentially with n.
So the circuit there is exponential.
The circuit here is exponential in n. Right, but if you add it to your 2 to the n, it's always exponential.
Okay, this result gives an into the complexity of find the basis of H.
Well, I mean, you see, you have to formulate it in the right way. It's not you cannot find the basis. You can do measurements at the end and get something. So what this will do is that you will measure. So if you have an eigenstate and you plug it here, you get the eigenvalue. But if you don't have an eigenstate, you have a linear superposition of eigenstate. It will give you an eigenvalue and will project in the corresponding eigenstate. And so but this will be random according to these probabilities. So this is what I told you before. That you read a book on quantum mechanics. You measure the observable Hamiltonian, it will give you an eigenvalue with this probability square and the eigenvector. And this does the job. That's basically what the claim is.
No, la realtà non una volta. Cioè, quello sarebbe trovato una io capito dell'esponenziale. Cioè, tu devi alla fine trovare tutti autostrati.
No, no, but that the worst case. The worst case. So anything. Then I know that it will be the variance of my observable, the conversion will be the variance of my square root group divided by the square root of the number of repetitions. I know that is an upper bound to the other that I will use the expectation value. I counted, and it's the worst case. Because if I have something better, is a repetition. Yes.
And I say that I and the next step run n plus and then minus plus the number and I see that the not put down.
Then mathematics is wrong. I mean, because this is the large numbers with a probability. This is the central limit theorem. So the central limit theorem, you have a Gaussian distribution of your result, whatever you do, because they are independent measurement, and it has to converge at this rate. If the central limit is right, then the probability that this happens goes exponentially down with whatever will never happen. It comes from the fact that you measure many times, you get an extra one because it's not possible to measure this observable in some way than anybody observable. You have to use something like that to measure. Waiting for a coffee? No, go ahead. No. This doesn't matter. I can't. Stop. Maybe I can. Yeah, okay.
that if you want to know the quantum magnitude, you have to square and yeah, sure. Yeah, sure.
Okay, so we're talking about quantum algorithms for the ground state, and I told you that the brute force algorithm would be just prepare some random state, and therefore typically the probability that if you measure the observable energy will be 1 divided by 2 to the n. So you repeat it many times, you will have it, and by the repeating then you will have the preparation of the ground state and the energy, and I told you that you want to measure this operator, this observable. However, this is difficult. I mean, yes, I forgot to say, something that is relatively kind of trivial. So you could say, well, why don't I measure each of them? Okay, so why don't I measure H1 and H2? Because these are local observables, so this you can measure locally very easily with a quantum computer. However, because if I measure H1, I will have an outcome, and I will project into an eigenvector of H1. But if the H don't commute, the eigenvectors of H1 will not be the eigenvectors of H. So I mess up the whole state. So I measure them individually is not the same thing as measuring the whole operator. And that's why you need a way of measuring the whole operator, and that's not trivial. Somebody gives you an operator and tell you how to measure. But this is exactly what this quantum phase estimation does. Given an operator, right? Then it measures the lattice remission, measures e to the I times this operator, the spectrum, and so on. And with that is where you can get the eigenvalues and the eigenvectors. So that's it. So now let me talk about another algorithm. I want to talk about a couple of algorithms, but just mention one because I will not have that much time. That it's very useful in practice, and that's the one that people are using in practice. It's called adiabatic algorithm. Also to prepare the ground state. So that's quantum adiabatic algorithm. And it's based on the adiabatic theorem, which is something that you can learn in textbooks. And it's a theorem that tells you, roughly speaking, that if you have a ground state of a Hamiltonian and you change the state, the Hamiltonian sufficiently slowly, then you will drag the state, and you will stay all the time in the ground state of this Hamiltonian that is evolving. Okay? So, in other words, so you have some Hamiltonian that depends on some parameter S, and so you put down the spectrum as a function of S, let's take between 0 and 1, for example, and you have here some spectrum, so you have some energy eigenvalues, so this is the ground state at S is equal 0, the eigenvalues are at S equals 0, and now you change S, then, so we would be solving this. So this will be just abusing the notation. So we're looking at the eigenvalues and eigenvectors for each value of S and for each value of S, and I'm plotting the eigenvectors. So this will correspond to a certain curve, maybe like something like that. Maybe some of them cross here. Okay, so maybe something like that. And the adiabatic theorem tells you that if you start with the eigenvector corresponding to the lowest eigenstate, namely with the ground state of H0, and now you change sufficiently slow, and this is what I will say later on, to H1, then your ground state, in the way in which you're changing this S of t, S is a function of t of the real time, then you will be at each point very close to the ground state. So you will be, the energy will always follow this curve. You go faster, what will happen is that you will jump and then you start creating some of the states. But if you're sufficiently slow, then you will go all the way and will land in the ground state of H of 1. So you start here with E0, let's say the ground state at 0. If you do it sufficiently slow, the technical word for that is adiabatically, then you will end up in E0 of 1. And so this automatically gives you a way of preparing ground states of Hamiltonians. So you give me this H, what I have to do, this H you're giving me, I say that this is, let me tell H tilde at S equal 1. If I find some path in the space of Hamiltonians that connects with some H of 0, which is a Hamiltonian that is very simple. For example, a Hamiltonian where you have single qubit Hamiltonians, for example, this could be like sum of sigma c, and right, there's a non-interacting Hamiltonian, then what you can do is to prepare in your quantum computer the ground state of this, which is the minus here, so it's all zeros. So you will prepare your quantum computer in the state of zeros, and now you change the parameter of your Hamiltonian sufficiently slow, and then the state at the end, if you do it adiabatically, will be the ground state that you're looking for. And once you have the ground state, then you know that we measure the observable, we'll repeat it many times, and then we'll have the solution to our problem. So the question is if it's always possible to do that. And of course, it's very simple to do that. For example, I could choose my Hamiltonian as a function of S, like, let me call it H0. You can call it like 1 minus S H0 plus SH. And that's a linear interpolation between the two Hamiltonians. So when S is equal to 0, it's H0, and when S is equal to 1, it is H that is here. And so this will do that. Now, the question is, what are the conditions in such a way that this works? And the condition, you can see it here graphically, is that if there is a crossing, then this is not going to work. So, it means is that there must be always a gap. You remember that I defined the gap? So, you can define the gap now for the whole path. And the first condition, such that it works at all, is that the gap is always positive, strictly positive. Then it will work.
The new H is not commuting.
Huh?
The new H, the final H is not commuting.
This is not commuting. No. So that's the problem, Hamiltonian. That's the one that I want to solve. And what I'm saying is that I take with one that I know how to prepare the ground state, and then I deform it to the final one. And as long as this condition is true, then I will arrive if I go sufficiently slow. So now how is sufficiently slow? So people have mathematical theorems for that, and they know that the time scales like some n, maybe to some power, but is polynomial in n, and like this gap, the minimum gap, let's call delta 0, or delta m, is equal to the minimum with respect of s of delta s, and depends on delta 0 to the power of minus 3, and 1 over epsilon, and things like that, square. And so, as long as this gap doesn't close too much, then it would be efficient. So if we want this time, delta m, delta m. So as long as the minimum gap only decreases like 1 divided by polynomial n, so if this is 1 divided by something that's case, let's just write it like that, poly n, then this will work. Okay, so you find a path such that this doesn't close. Now you increase n. Okay, you find the path, and then you increase n, and the path, increase n, increase n, increase n, and maybe this is closing and closing and closing. So as long as it doesn't close too fast, as long as it doesn't close like 1 divided by exponential, then this is going to prepare the state in polynomial time. So this is an efficient algorithm. So now what happens in practice? In practice, now we can go to physical systems, and then we know that in physical systems, when you have a Hamiltonian, then you can have different phases in your phase space depending on the parameters of your Hamiltonian, and many phases are gapped. So many phases have a gap in which this is a constant, even in the thermodynamic limit. This is what you have, I mentioned that yesterday, so exponentially decaying correlations. And when you start moving from one phase to another one, you will go through a phase transition. And you have a phase transition, then we know certain cases in which we can study this phase transition. For example, you have criticality. We know that you have a critical point, and this is described in terms of some conformal field theory. And in the conformal field theory, then we can get how much are these gaps. And these gaps in these critical theories scale like 1 divided by n to the critical exponents. So its case we need as 1 divided by polynomial n. So for all these problems, this would be an algorithm, would be polynomial. So maybe if you want to explore and you want to study something, some transition, and you don't know what it is, then what you can do is that you can try. So you can try to do the adiabatic algorithm, and so maybe it works and it doesn't work. So how do you know if it works or it doesn't work? Well, there is not a systematic way that will give you completely confidence that you know it, because so it may happen that there is a crossing and then you go very slow, but you always cross it and you don't know. So, but one way of doing it in practice, so now I'm talking more about practitioners, you have a quantum algorithm running the adiabatic theorem, you do like people do with numerics. So you can go back and forth. So if you're adiabatic and then you go forth and then you go back, then you have to end up with the state 0, 0, 0. So you can go forth, then go back and check that you're 0, 0, 0, 0. And then you can go maybe slower and go back and 0, 0, 0, 0. And if you're going through you have a non-adiabatic transitions, then when you go back, you end up in some orthogonal state and will go to some other state. So this will give you some kind of evidence that this is working, and so that's what people expect, that these quantum algorithms, based on the adiabatic theorem, will be used in practice, that you will just run it. If you know that there's a critical and you want to explore it, then you know what is the scaling, and then you can go like sufficiently slow, but it's still polynomial, and this will work. If you don't know, you want to explore, then you have to use, like people use with numerical algorithms, you're doing solving some differential equations, or partial differential equation numerically. So how do you know that it works? You run forward and backwards, and if you go back, then you know that you don't have errors, and so you use these tricks. So again, so this is a quantum algorithm which works, so it's efficient under a promise. So you have to have a promise, meaning that somebody has to ensure you that this gap decrease like 1 over poly n, and if it's like that, then the algorithm will work. Now you could ask, so what happens now with classical algorithms if we have the same promise? Because we have to be fair and not compare the quantum algorithm with some condition is fulfilled with the classical algorithm if this condition is not fulfilled. Well, I mean, as far as I know, and I think that it's really true, I mean, the fact that you have some gap in your Hamiltonian in this form does not help you in classical algorithms, no? Unless you are in one dimension. System with local interactions, and the gap here is not 1 over poly n, but is constant, then the problem is in BPP. It's classically efficient. If it's not constant, this has not been proven. So if it's 1 over n, like you have a critical point or something like that, it's not done. And if you're in higher dimensions, even if it's constant, then we don't have any promise about algorithm. So that's a case in which now, with this promise problem, so you have the ground state, and add here the condition that there is some adiabatic path to some other Hamiltonian, which is gap that is brought like 1 over poly n, this problem would be like in BQP, but not in BPP as far as we know. Okay, so now I will mention some other quantum algorithm, which is a variation of this quantum algorithm. It's basically some idea, and that it's relatively popular as well in quantum computation. And well, I mean, of course, I mean, this adiabatic algorithm, at the end, the quantum algorithm has to take your time-dependent Hamiltonian and evolve your state according of your quantum computer according to this time-dependent Hamiltonian. So it's using the quantum algorithm that I told you before for dynamics. Okay, so that would be like the dynamics, like a subroutine, if you want, of this, because it's using that one, and I told you that that was efficient. So that's working. So the other one. Is called under variational quantum eigensolver. And there are different versions of that, but let me tell you what is the main idea. The main idea is that imagine that I take the quantum algorithm and the variational quantum algorithm, sorry, the adiabatic quantum algorithm that I told you a second ago, and you remember that we say that we built a specific path, which was this 1 minus h0 plus h times s, and then you can write this like h0 plus s times h minus h0. And now, with the adiabatic algorithm, what we'll do is that we'll evolve with respect to this Hamiltonian with this s changing as a function of time. And for that, you will do this trotterization that I told you before. We will divide it in small time steps. And so you may think that you evolve a little bit with this Hamiltonian, trotterizing it, then you evolve a little bit with this Hamiltonian, then you evolve with this Hamiltonian, then a little bit with this Hamiltonian, and so on, like trotterizing every time. So one could say, so if you're at the end having that your evolution is e to the minus h0, I h0, some t0, which is very, very small, it is t divided by l, so sufficiently small, so it's that we can do this commutation. Then we have e to the minus I, after that we let e to the minus I, h minus h0 for some time t1. And so this is, let's say, the evolution that at the end we are doing, by changing just as a function of time, these quantities. We're applying these now properly trotterizing the algorithm. So, and these have to be kind of very, very small, like infinitesimal, these time steps, in such a way that now we can use the quantum algorithm and totalization and everything else. So I can say, well, so if at the end we are applying this Hamiltonian and this Hamiltonian and this Hamiltonian, we call it H1, we sometimes say, why don't I try to go faster and make these times bigger, not of the order of 1 over L, or the order of 1, or something that is, and then the algorithm maybe is faster. And so what you say, so what should I choose here? So, well, what you can do is take this as a variational parameters, and then use the variational principle that I was telling you before. So now the idea is that you say, okay, this initial state, which were the 0, 0, 0, let me call this a state that now depends on these variational parameters, T0, T1, Tn. So if I change these parameters, I'll have different states. So I have a parameterization of the states that I'm creating in terms of these times that I'm using. Now what you could do is that for each value of the parameters, you can prepare the state with the totalization and with everything that is required, and then measure the energy. You could compute now what is the expectation value of the energy of your final Hamiltonian, which I think I call it, H. Okay? And so how do you measure that? Well, when we say, well, one would need this quantum, because here we are doing into the eigen, we don't want to have filtering measurement. We want to compute what is the expectation value of some Hamiltonian. So what you can do is that you can measure these parts independently. So I can measure H1 first, repeating many times, then H2, repeating many times, then H3, repeating many times, and sum all of them, and this would be this value. So for that, we just can do it just by measuring each of the locals in independent experiment, measure many times, and then we will obtain this expectation value with some errors. So now I have certain energy, and what I can do is variational. So I can measure this with whatever errors, with this, I could say this is an energy that depends on these parameters. Now what I can do is that I can change one parameter, and so I change T0 to T0 minus epsilon, and then repeat. And so now the energy will change. So if the energy grows, then I don't take it, but if the energy goes down, then I take T0, and now change another parameter, and then I change another parameter, and change another parameter, so I will be moving, and the energy, this expectation energy as a function of my parameter, which is called P, so I will always move down. And if I take the optimal one here, then I will go to some value, and this value could be an estimation of the ground state energy. And if now, of course, if I would take many parameters, then I know that this energy would be as good as the one given by the adiabatic theorem, because this includes the adiabatic theorem. The whole is that without having to take these many parameters, taking fewer parameters, then you already reach something like that you see that it state, and therefore there is an algorithm that would be faster and would produce this energy, but of course you would know what is the energy. If you stop here, then you have the state. You can create the state, and once you have the state, you can measure your observable, repeat it many times, and then answer the question that we were posing at the beginning. So, yep.
Your minimization is conditioned by the fact that the sum of P0 must be of this time.
Right. So you just put this in between 0 and 1 or something like that. Yep.
So you are not really free to, at least the last one, you are not free to change it, minimize, because otherwise you break this.
Right. I mean, of course, all these Hamiltonians have recurrences. So if you would take a time that is too long, then you will have a recurrence, so this cannot go always down for a possible larger times. But I mean, you can analyze that and then put it as you have some limits on your parameters, and you take in between some numbers and some numbers, and this is included here. So, okay, so that's a method that includes the adiabatic method, but it may be faster in practice. This has a name, and it can be used not only for this Hamiltonian problem, but for some other problems where there is some optimization. So there is some function here, it doesn't have to be an energy, there's an optimization problem, and then you're optimizing with respect to that. And this has a name, this is called QAOA. I don't remember what are this acronym, but anyway, quantum adiabatic or quantum, I don't remember. But anyway, so now what you can do is that you can say, well, but why do we have to take here H0 and H1? Why don't we take some other gates here? So what you could say is that, oh, well, let's take now the same idea and don't restrict to this H0 and H1. Let's take an arbitrary quantum circuit. Let's put here some gates, for example, 2 qubit gates, like that. Each qubit gate is completely determined by a constant number of parameters, by 10 parameters or 12 parameters. So there is some parameters here, P1, it's a vector, so there are several parameters. And do the same thing, so let's measure here. Let's compute the energy, and then feedback, and take the parameters, check the parameters in such a way that you minimize the energy. And now, I mean, this is a generalization that goes under the name of this variational quantum eigensolver. And so, I mean, in principle, this could work well. In practice, it doesn't work that well as far as I know, but sometimes it works. So you will see that people have taken now the existing quantum computers, this kind of few qubit quantum computers, taking a problem, maybe of chemistry or anything else, written the Hamiltonian and apply this, and then you will see many of these results based on this algorithm to find the ground state. Okay? But again, so I want to distinguish what is a heuristic and what is promise. The quantum adiabatic algorithm is a promise, so you know that it will take some time as long as your gap fulfills certain condition. This once here is not a promise, it's a heuristic algorithm, which you cannot say if it will work. However, I mean, many times it works very well, much better than any promise, and so this is why people are trying. And that's also why you will see that there are many startup companies, many people just trying to solve optimization problems using this kind of algorithm with a different circuit, with different ideas, because maybe some of the problems that they try to solve, I mean, work, I mean, even if there is no promise, whereas with classical computers it may take a longer time. That's the hope, one of the hopes of quantum computation. And so I want to move on now to the last part of this presentation, and that's the finite temperature. Finite called finite energy and finite temperature. So here, I mean, we are going to add temperature, but I will reformulate the problem in terms of energy. So in the jargon of statistical mechanics, I'm going to work with the microcanonical instead of the canonical ensemble. But anyway, I have to redefine the problem, and then what I want to do is that building the microcanonical ensemble, then you can get a canonical ensemble by sampling different energies according to the Boltzmann distribution. So. As you remember, we have this spectrum, and this goes from -n to n, and then we have whatever these are these eigenvalues in the spectrum. Now, what the question that I want to ask is: imagine that I fix the energy here, and so I want to have the properties, so the expectation value from observable for a given energy. That would be like the microcanonical ensemble. But I want to scale the problem. And so this means that I would like to fix the energy, but if I scale the problem, I will have to change the energy. So what I'm going to fix is the energy density. So I'm going to define E as some E divided by M, the energy density, in such a way that I fix this E, so this will be E times M, the energy density, and then I can scale everything. So I fix this E, and then I scale my energy, and I would like to have this eigenstate. Macrocanonical would be to take an eigenstate corresponding to this energy and compute the expectation values of all with this eigenstate. However, this spectrum is discrete, and therefore, if I choose one value, it will be 0 probability that I have an eigenstate in this value. So what I will have to define is some region of energies in which I'm interested. So I will take here some region which will have a width delta, and the problem has to be formulated also in terms of delta. So what I would like to do is to find a state. So the problem, the way I formulate it, is that I would like to find a state which has this mean energy, so the expectation value of the state psi is equal to E times M, and it has a variance smaller or equal to delta. And given this state, I would like to compute the expectation value of this observable with a precision epsilon. So you see, now I have a lot of things. I have to give you the lattice, the number, the observable, the prescription, the Hamiltonian, not the temperature, the moment I'm not talking about temperature, but the energy density and the variance of the energy that I want. And so that's a problem that you can, that we want to solve with a quantum computer. But first, let's get a little bit of feeling of what does it mean, this delta. So imagine that I prepare a product state. So imagine that I'm able to prepare a product state at this energy. Okay, so that I have a product state psi is equal to this product that I mentioned before, in such a way that the expectation value is the right one. So what is the variance of the product state? You can compute the variance, it's very simple. And I wanted to do it, but I don't have time to do it. So you see here that you take h squared, then you have products of all possible h lambda and h lambda prime. And like before, it can happen that there are some products which overlap and some that don't overlap. If they don't overlap, then the expectation value will be the product of the expectation values. So they will cancel with this part here. So this means that you will only have contribution from the parts that are overlapping with each other. This will be different than 0. And how many of them are there? Well, there are n, because for each of them there are a few neighbors that overlap, and you have all the positions. This means that this variance of this product state, so the variance of this product state, the variance in the energy, is scales like n. So it's actually many smaller than the constant like an n. So what it means is that I should define maybe square root. Let's call it t squared, delta squared. So it means that if this delta is of the order of square root of n, this problem is trivial. Because I could just get a product state and then compute with this product state the energy, make sure that this energy is this value with this product state, and then once I have a product state, computing the value of the energy is very simple classically. Right? I have to take the product state, I can compute everything very efficiently. So this means that the problem will get difficult as long as my delta that I'm asking here will be smaller than square root of n. For example, if it's of the order of 1, or it's of the order of 1 divided by n, or 1 divided by n squared, or something like that. Okay, so that's the first point. So that we want to solve this problem for the case in which you cannot solve it classically. And now you can go to classical algorithms which solve this problem. There are some algorithms that solve this problem. And this computational time classical algorithm that solves this problem is case that the minimum of the exponential of n, let's say 2 to the power n, or 2 to the power 1 over delta. And so you see that if the delta is even of the order of 1, there can be classical algorithm that solve that. However, if delta is of the order of 1 divided by n to some power, we call poly n, then this is difficult with the classical, with existing classical algorithm. So you know that I'm always referring to the state of the art of classical algorithm. Maybe tomorrow somebody comes for this algorithm and then has a better algorithm, and then this will change the class where it is. No? So that's where is the challenge. So to compute now this quantity with variance that scales like 1 divided by poly n. And for that, there is a quantum algorithm that does it, and therefore there is an advantage with respect to it. So now, from the physics point of view, so if there is here some people working on equilibration or in statistical mechanics, then you can go to the problems where we know something to know what are the interesting deltas for the physical point of view. And for example, if you accept what is called the ETH, the Eigenstate thermalization hypothesis, meaning that if you start with some initial state of some interacting system, and if you look at some subsystem, then after some time it looks like a thermal state, like a Gibbs state. This is the thermalization hypothesis. If this is true with the formulas that people have conjectured and that people have checked numerically, then you see that the interesting regime is when this delta is of the order of 1 over n or 1 over n squared, typically. That's where the expectation values that you will compute here, this is sufficiently narrow that you will get the microcanonical value. Okay? So microcanonical doesn't have to be exactly the same thing, but it has to be but some states that have similar properties, and that's the one that you get the microcanonical value. So that makes sense that, I mean, the challenge that you want to do with a quantum computer makes physical sense. You want to go to a regime where classically, where there's physical context that you can get there, but classically is difficult. And so for that, we are going to give you a quantum algorithm. And so I will not have time to explain it in detail, so I will give you what is the idea. Okay, so the idea is based on 3 steps. The first step is prepare a state with the desired energy. Prepare a state with desired energy. For example, if the energy is not too low, then a product state will do the job. Because product state you can cover a range of energies that is large, is not the whole spectrum. However, if the energy is getting very low or very large, then you will need a quantum algorithm that prepares a state of low energy. And for that you can use the ones that I told you before, because they prepare the ground state. So again, if you would have that the Hamiltonian that somebody gives you is gapped, or the gap decreased like 1 over poly n, then it will be efficient with a quantum computer to prepare this state here. But if you have this state, then you can easily prepare a state with any mean energy. When you start here, you start flipping qubits, and every time that you flip a qubit, then you increase by 1 the energy, you flip it less, you can go continuously to states which have the energy. So this preparation of the energy gives you some restrictions, namely that either your energy is in some interval in which you can prepare product states, or you want to prepare, you're asking questions about very low energies, then it has to be a problem for which you can prepare these states with the adiabatic algorithm that I told you before. So that's the first condition. Now, let's take the case in which you prepare a product state to make it simple. Then we know that now we have the right energy, however, this variance is too big. It's a square root of m. And we want to have a variance that is narrow. So what can we do? Well, we can filter the same way that if you have light of many colors, and you want one color, you put a filter, let's put a filter. So what can be a filter? So what we can do is to take our initial state, this product state, let's call it psi 0 maybe, and let's filter with delta. So what I could do it is mathematically if I apply e to the minus h minus the desired energy squared divided by 2 delta squared. That's a Gaussian filter. So what this will do is that if this is a linear superposition of states, so it's a linear superposition of these states, this will give, it will kill all the energies that are far from epsilon more than delta. And so you can show with some little bit of effort that the state that is here, if you properly normalize it, will have a width which is the desired delta that you want. However, you run into a problem. The problem is that this operator is not unitary. And therefore, this cannot be created with a quantum computer. It's very non-unitary. So now, the second step tells you how you apply, can you apply this filter with unitary operators. And the idea is basically to do some Fourier transform, or if you want, I can give you another, which is more, a little bit more intuitive. You can approximate a Gaussian with a cosine very well. So you have some Gaussian like this one here. You have e to the minus x squared divided by, say, delta squared. This is like a cosine of x. I have to do it right. Maybe there's a 2 here. A cosine of x to the power, this is 1 over delta squared, I think. So why is that? Because you see, this cosine you can Taylor expand it, and so it will be like, maybe the drawing. So you have a cosine, the cosine goes like that. Like that. And you see, if you're restricted to this region, so you take x smaller than pi divided, let's say pi divided by 2, so you're in this region here, then if you take some power, then everything that is here is damped down. So you will get something that goes like that, and that goes like that. And here it has the correct behavior, and when it's small, it's so small that it doesn't matter if you take any power, that this is the same. So you take the difference between these two, you can upper bound very well. So the idea is, instead of taking this Gaussian filter, let's take a cosine filter. So let's take a cosine filter, so we replace this Gaussian by a cosine, because it does exactly the same job, of h minus z squared. And then, since you want that it doesn't go over pi half, this is true, it's pi half, and you know that the spectrum of h goes from minus n to n, then you will have to divide here by n. And so you will have to put here something like n divided by delta squared, maybe there is a square here. Something like that. And now, the cosine is e to the I, but e to the minus I. You use the binomial formula, and so this can be written, I'm not doing it just very precisely, but this can be written as a sum from n equal minus something like, would be like n divided by delta, or something like that, to n divided by delta of e to the I h minus e divided by n times, now you have here something like m. So what I'm doing is writing basically this filter with some coefficients. These are the binomial coefficients. Well, I mean, there is some binomial coefficient you can compute what is here. So I have a sum of exponentials, and so now these exponentials are unitary operators. So in the second step, and the number of terms that you have here, you see that is still polynomial in n, because you have n divided by delta. Delta, you want 1 over n, so it will be like n squared, something like that. So you have that this is a sum of unitary operators. So what you would like to do now is to start with your initial state and create a linear superposition of a state where you evolve with your Hamiltonian some time 0, then some time 1, then some time 2, some time minus 1, time minus 2, and so on, and to have a superposition of that. And so in principle, you could do that. However, since this is not a unitary operation, then you will have to do something to make it not unitary. And in principle, you can think of what this would be. This could be measurement, but if you have measurement, then you have to take into account that the probability of success may be very small, and then everything scales down exponentially. So that's why there is the third step, that in order to prepare something like that, instead of preparing something like that, what you're going to do is to do something different. And that's, so maybe I write it here. What you say, well, at the end, I have this state, it can be some like e to the minus I, h, t, n acting on psi 0, where this n runs from something to something. That's the formula that we have, where this time is either 0, 1, 2, 3, 4, whatever. That's what we want to have. Then you say, well, actually, why do I want to prepare the state? What I want to solve, the question that was asked at the beginning, is what is the expectation value of O? So let's compute now mathematically the expectation value of O. And so for the expectation value of O, then what you will have to compute is psi O psi divided by the norm, because the state is not normalized. So you have to normalize it. And now we can write down with that formula. So you see that there will be here a sum of n and m, and then there will be the psi 0 e to the I h t n O e to the minus I h t n psi 0 divided by sum over n and m of psi 0 e to the minus I h and as t n times t n times psi 0. So this is what I want to compute. And then you realize that if I defined this as some A, so we call it B, that depends on Tn and Tn, so it's right, N and M. And this, we call it like A that depends on N minus M, so let's put there N and M as well. Imagine that you're able to measure these quantities, and to measure these quantities with a quantum computer, each of them independently. Then what you could do is to compute them, measure many times, and then put them in this formula and compute everything. So the idea of this algorithm is not to prepare the state and then measure something, but rather to say, well, if I want to compute the expectation value, I don't have to do that. What I have to get is how much is that, and how much is that for different values of n and m. And if my computer is able to do that, then I will be able to compute this quantity. But you see that, I mean, let's look at this, what is here. So this is what is called a log-speed echo. So you start with some initial state, you evolve for a certain time, and then you look at the overlap with the initial state. So it's that you start with your quantum computer, then you evolve, and the evolution you do, this is a product state of the state that you prepare, then you evolve, and for that, this is like the dynamics, so you use the quantum algorithm for the dynamics, and once you have, instead of measuring some observable, then you check you have the initial state. So if it was a product state, you will measure each of the individual qubits, and then you will check if this is equal to the initial state. If it's equal to the initial state, you give a 1, if not, a 0. You repeat it many times, and you will do that, you will get the absolute value of this quantity. So that's how you will measure the absolute value. Now, this quantity is, in general, complex, so you'll have to get the phase. And now, I have time to get it, but the phase can be, there's an algorithm to measure the phase, which is also efficient. It's called Hadamard test. It has a Hadamard test, which is similar to, again, so you have a qubit, then you apply a control unitary, and then again you measure this qubit, and this qubit will give you the phase. So you need some control unitary, but this can be done with the algorithm that I was building on the previous algorithms, and you will have to repeat it many times for each value of n and n. You will have to repeat it, and of course the epsilon will accumulate. So the error that you will have to do will not be will not be epsilon in 1, but it will be epsilon divided by, I mean, the number of measurements that you do, because you will add this error, but still everything is polynomial. And so at the end, if you do this algorithm in the quantum computer, you perform this algorithm in the quantum computer, the computational time for this algorithm is here. The computational time is polynomial in n in 1 over delta n in 1 over epsilon. So it's a polynomial algorithm. So you still have 5 minutes?
Couple of minutes, yeah.
Okay, a couple of minutes. Okay, so this gives you the mean energy. Now, how do you do the final temperature from this algorithm? So actually with that, you can use it to compute also the canonical ensemble, the final temperature. And the basic idea is to use this as a subroutine. So I will not explain it here, but yesterday I told you that in the Monte Carlo, you want to sample in Monte Carlo, you will have to compute things like that I called yesterday P of n. If you're able to compute P of n efficiently, then you can sample according to that. And I told you that typically quando Monte Carlo, you're not able to do that because you have the sign problem. But it turns out that this algorithm can be now rephrased. So this into the, you just do a couple of steps, and you can rephrase it into computing this Pn can be also written in something like that. So this means that in practice, what you would use in order to compute now canonical ensemble is that it's very complicated. So you will take, for one configuration, you would use this algorithm, which uses itself many times the dynamical algorithm to get these ANs, BNs. With all these A and BNs, you will compute this P of n. Now you make a change, and then you do the same to compute the P of n, and according to Metropolis algorithm, you accept or not accept. And if you do that, this will give you the sample, and with this sample, then you can avoid the sign problem, and therefore get some expectation values. Still, now, whereas this one is rigorous one, so you can prove that for solving the finite energy, this is the computational time in a quantum computer. In a quantum computer, if you use this other for finite temperature, even though you avoid the sign problem, still you could have sampling problems. No? That still you're sampling very well, but your Metropolis algorithm is not ergodic, so doesn't sample all the probabilities, and it can still happen, and for that you will need some extra conditions. And I think that with that, the chairperson here is telling me that I am now finished, so thank you for your attention, and I'm open to questions.
The first question is about this typical quantum annealing study. I imagine that the linear interpolation between the two methods is the standard, but maybe you may consider some smarter choice in order to avoid this level problem.
That's right. So of course, the gap will depend on what is the path in the Hamiltonian, and there are many paths. And in fact, I believe, I'm not sure about the statement, but I think that it's true. It's possible to prove always that as long as the final Hamiltonian is gapped, or has a gap, 1 over poly n, there always exists a path that has this gap. This meaning that this doesn't close. However, to find it is computationally hard. It's as hard as solving the original problem. So that's why, in practice, if you take the linear interpolation, then you want to do it better. I mean, if you're familiar with the adiabatic theorem, it will tell you that the error depends on the derivatives at the at the beginning at the function. So you would like that this function s of t has as many derivatives, or the derivatives that are equal to 0 at the beginning, at the end, because then it improves the algorithm. So basically, in some quantum algorithm, a big part of the error is at the beginning when you start, and at the end when you start. It's like if you try to move a pendulum adiabatically, right? At the beginning you just move it, and then it's where the error is more adiabatic, and at the end you stop. And so then you do it right. And so this is why, so we will have the time to show it here. Actually, you can take Rayleigh functions, and these Rayleigh functions are functions that have all derivatives equal to 0 at the beginning and at the end, and they still prove. And you used that some time ago. What we even proved that the adiabatic algorithm that I told you that it scales like n, actually can scale like log n, so you can get better parts and so on. So when I say that, in practice you don't care about that, you probably will try, and there will be one that will work because the space of all possible paths is so big that it will be impossible to find the best one, but maybe you can find a good one. Now what happens in many cases, I mean, I didn't mention here, is that there are problems for which you can prove, and people have proven, that the gap for some paths decreases exponentially with them. So there are some problems, and typically, now if you want to solve not many body Hamiltonians of the kind that we have in physics, but the ones that appear in optimization problems, these are called satisfiability problems, symmetry problems, and so on, then, I mean, all the gaps will have this exponential small, and that's why it's very difficult, even though there is a path that may be good, it's very, very difficult to find it, and so in practice, none of the methods that I mentioned here will be efficient. But yeah, indeed, so I mean, you can play with the path to improve it, and so people do that, try to find a good one, but it's impossible to find what is the best one.
Can you ask me the second question also?
Yeah, sure.
Okay.
Second question, and then you ask me.
Going to this method here, I have some concern. Maybe you can clarify about the normalization that is the Loschmidt-Echo, right?
Yes.
So because this is a very small quantity.
It's a very small, but you can prove that it's still Suffi polynomial, 1 over polynomial. So the times that you have to run it,
yes,
I mean, it's a sum. And so for small times, it will be big. And now you're adding something that may be small, but this is getting exponentially small. But of course, when it gets exponentially small, you will add 0. So the norm still will be a number that will be sizable. But of course, many of the terms will be very small, but you will add 0. So it's a sum.
Yeah,
but you're saying that some of the terms will be very small.
Okay, but aren't all the terms very small?
No,
because
when Tn is equal to Tn, this is equal to 1.
Oh, you also have some that are very close. Okay.
Right. So they're all possible.
Yeah.
And so, right. So when
I was not thinking. I was looking just at one time. If it was only one time, then we would be in trouble, right? Because
no. They have to sum with respect to all possible time. And so what happens is that you can take this quantity and the sum and to prove that even if you are summing and adding, that is always larger than 1 over polynomial. And that's why it allows you to have that.
Okay. My second question is also related with the adiabatic theorem. Suppose that you have the problem of computing the geometric phase or the adiabatic phase in this case, maybe non-Abelian phase. Do you have a quantum algorithm for doing that?
Yes, because you can use superposition. So the idea is to use what is called this Hadamard test. You start with a qubit, and you put a qubit in superposition of 0 and 1, so 0 plus 1. And then you have a control evolution operator. So this means that the 0 path doesn't evolve with the Hamiltonian. The 1 path goes according to the adiabatic algorithm. And now, if you measure this, this qubit, then it will give you some information about the phase that you have accumulated. Now, of course, this phase will accumulate the dynamical phase and the one corresponding to the holonomy or whatever. But you can extract, you can measure them independently and so on. So there are ways of doing that.
First of all, thank you very much for this very interesting and rich overview. Just a little question, because as already asked. What is the present regarding the qubits, the single qubit, the phases and continuous variable? What is the present experimental limit, more or less, which you can divide the unit circle, and you can realize, you can distinguish phases? What is the present experimental level?
Okay, so I'll tell you that you can do 10 to the minus 4 or something like that. So e to the I to 10 to the minus 4 regularly with atomic experiments already for many years. And so the limitation it's more in the error that you will have in the lasers or whatever you're using in order to drive them. Rather than that, you have to stabilize it. But already with something to the minus phases of 10 to the minus 4, you see, if you will need a phase that is smaller than 10 to the minus 4, then you cannot do this phase and put it in the error budget, right? And then the error budget will have an error of 10 to the minus 4. And so since your error budget typically is epsilon is going to be 10 to the minus 2 or 10 to the minus 3, then it will not be necessary to do it in practice.
About the adiabatic theorem, suppose you don't have an Hamiltonian with a certain gap that is suitable for using the adiabatic theorem. Can you use some sort of kernel, maybe, to project the Hamiltonian in either space where maybe there is the gap?
Right, but projecting is non-unitary, and projecting means that you can do a measurement of something that is non-unitary, and whenever you have a measurement, then you have a certain probability of success. And since you have a many-body system, you have n qubits, you have to do n measurements, and the probability that you have the right result will scale exponentially with it. So, I mean, if you ask me like that, I say, well, it's possible to do that, but if you do it naively, this will already give you some exponential probability that you are successful. People, what I have done, you know, if you're familiar with the adiabatic theorem, in the adiabatic theorem, so you can have a kind of Sino effect, which is basically that you're projecting continuously into this ground state without measurements, because you can kill some phases. So basically what happens when you are building from the ground state to an excited state and you are building coherences, if you depolarize something, then this kills these phases, and this equivalent like if you were projecting into this ground state. However, I mean, this actually gets a little bit better. It gets I think that the scaling with the gap, like 1 over gap squared, not 1 over gap to the cube. But it has a limitation, and that's another funny thing of the adiabatic theorem. You're familiar with that. In the adiabatic theorem, if you do it with finite time, you would assume that if you end up in the final state with a high probability, then probably in the middle you're in the right state. That's not true. In the adiabatic theorem, actually, you go away from the ground state, even though you think mathematically you will do, you go a little bit away. So in fact, people, you can derive a kind of effective Hamiltonian for an adiabatic path and some adiabatic time, and the adiabatic theorem is in the ground state of that other Hamiltonian. So you're trying to use a projector, assist the adiabatic theorem with some projector, your projection. You will not do that well because the adiabatic theorem will work only through some other states. And so these things are together and makes that you cannot do it perfectly well, and the scaling with the gap is 1 over delta squared. And so people have proved now mathematically that in any adiabatic theorem, it will scale like, the best case can be 1 over gap or gap squared. So they found some particular instance in which you can prove that if you could do it faster than 1 over delta squared, you would be able to solve a problem that we know that you cannot solve with a quantum computer. Actually, some Grover problem.